Imagine waking up early one morning, grabbing a cup of coffee, and instead of heading to the airport for a trip around the world, you board an elevator, one not just bound for another floor or even just another city, but for outer space itself. It sounds like the stuff of science fiction, an idea plucked straight from the pages of a futuristic novel. Yet the concept of a space elevator has been tantalizing scientists, engineers, and dreamers for over a century. But what if we actually went ahead and built an elevator to space? What would it mean for humanity, for our planet, and for our journey to the stars? To fully appreciate the impact, you must first grasp what a space elevator actually is. At its heart, it is a tremendously ambitious structure. Stretching from the surface of the Earth all the way out to geostationary orbit, nearly 36,000 kilometers, a little over 22,000 miles above our planet. To visualize this, picture a thin thread, impossibly long, anchored firmly to the equator on the ground, extending upwards past the clouds, past commercial planes and satellites, all the way to where the pull of Earth's gravity and the outward force from spinning around our planet balance perfectly. At the very top of this thread sits a counterweight, ensuring the structure stays taut, while a series of climbers, or specialized elevator cars, move up and down the ribbon at astonishing heights. The first practical step toward this extraordinary dream is materials. Conventional construction supplies simply can't handle the job. No known material like steel or titanium could withstand the colossal tension forces placed upon a cable stretching such an immense distance. The answer lies in the realm of ultra-strong materials, most notably carbon nanotubes or graphene. These materials, at least in theory, possess the kind of tensile strength needed for the job, far surpassing anything humanity has yet mass-produced. If, someday, we refine the technology to produce these nanomaterials in lengths of thousands of kilometers, then the most daunting physical barrier will have been crossed. With a suitable material available, construction would begin at the Earth's equator, most likely from a mobile ocean platform, to avoid storms and minimize risk from catastrophic events. The cable, thin but unimaginably strong, would be slowly unspooled upward, guided by robotic climbers that carry additional lengths of material, gradually reaching orbit. Once the counterweight is in place, the cable would be kept under constant tension by both the gravitational pull of Earth and the outward centrifugal force generated by the planet's spin. Now, picture the moment when the elevator is operational. People from across the globe would arrive at the base station, gaze up at the cable stretching beyond visibility, and step into an elevator cabin. Pressurized and roomy, these cabins would glide up the ribbon at a steady pace, perhaps 200 kilometers per hour, offering passengers a chance to watch Earth shrink beneath their feet as they traverse layers of atmosphere. The energy required to move cargo and people up the elevator wouldn't come from hauling enormous rocket fuel reserves. Instead, climbers could be powered by laser beams shining up from the ground, or by solar panels mounted on the elevator itself. This process would be dramatically more efficient and far less polluting than traditional rocket launches, offering an elegant, quiet ascent to orbit. Once at geostationary altitude, passengers and cargo could be transferred to satellites, moon-bound ships, or Mars missions. What would happen next is nothing short of revolutionary. Space launches today cost tens of thousands of dollars per kilogram sent into orbit, mostly because of rocket fuel, engineering limitations, and safety requirements. The physics of rocketry impose ironclad limits that we have chipped away at, but never broken. But a space elevator sidesteps these constraints. By riding up a cable, payload costs could plummet to perhaps a few $100s per kilogram, or even less, if the infrastructure becomes widespread and automated enough. With access to orbit made almost as easy as booking a plane ticket, the implications ripple outward, transforming industries and opportunities. Satellites could be deployed and serviced at a fraction of today's cost, heralding incredible advances in communication, climate monitoring, disaster response, and scientific research. Space stations could receive regular supply runs, personnel rotations, and even luxury goods with a level of safety, reliability, and frequency unimaginable with rockets. Microgravity science, medicine, and manufacturing would become everyday undertakings. Consider the human element. Researchers, educators, students, and even tourists could travel above the sky. Trips into orbit, once reserved for a handful of elite astronauts, would be open to tens of thousands. Scientists could work aboard habitats in orbit, performing zero-gravity experiments without enduring the ferocious physical demands of rocket launches. Students might take field trips to the edge of the atmosphere, gazing down at Earth from a vantage point once accessible only through textbooks and imagination. From the top of the elevator, the gateway to the solar system stands wide open. Launching missions to the Moon or Mars traditionally requires enormous energy to escape Earth's gravity well. But from geostationary orbit, getting to these destinations is much easier. Robotic cargo carriers could ferry equipment for lunar bases, Mars landers, or asteroid mining with a frequency and safety that could revolutionize off-world industries. Giant ships, built in microgravity from resources gathered in space, could embark for Earth's neighbors without ever needing to withstand the violence of launch. There are more subtle, yet profound consequences as well. By lowering the barrier to accessing space, the elevator could serve as an equalizer among nations. No longer would only the wealthiest countries with advanced rocketry be able to place payloads in orbit. Countries around the equator, Colombia, Kenya, Indonesia, to name a few, would have prime locations for space elevators. Collaboration and competition could flourish as investment and scientific interest flow to regions that were once cosmic bystanders. But, as with all dreams that reach so high, the risks are just as lofty. The cable, though strong, would be vulnerable to natural and artificial hazards. Micrometeorites, lightning storms, hurricanes, and even the orbiting debris already populating space could threaten the structure's integrity. Defense and maintenance strategies would be critical, perhaps a combination of advanced coatings, self-healing materials, orbital debris mitigation, and constant robotic patrols to detect and patch any damage. If a break should occur above geostationary orbit, the upper part of the cable would fling outward along a tangential path, while the lower portion would tumble back to Earth. Careful engineering and automated emergency protocols would be essential to avert disaster. Security brings another layer of complexity. The elevator, as a key piece of planetary infrastructure, would be tempting both to terrorists and to nations seeking asymmetric power. International treaties would need to be forged, laying down rules for construction, access, maintenance, and emergency response. Like the International Space Station, governance would require collaboration on a scale never before attempted. On a more everyday level, the technology stack behind a space elevator would need to evolve rapidly. The elevator climbers themselves would be marvels of engineering, able to function in a vacuum, weather ionizing radiation, and keep passengers comfortable for several days as the slow climb progresses. A logistics network rivaling global aviation would be born overnight, ensuring energy is supplied flawlessly, schedules are kept, and emergencies are managed with the safety and calm we expect today from air travel. The potential for lunar or Martian elevators is tantalizing too. The Moon's lower gravity and lack of atmosphere mean that elevators could be constructed from less exotic materials. An elevator on Phobos, Mars's tiny moon, could serve as a stepping stone, enabling low-energy transfers between Mars, its moons, and deep space. A true interplanetary highway system might arise, shuttling materials, people, and knowledge across the solar system at a pace and price never before imagined. Environmentally, the impact could be remarkable. Modern rocketry leaves behind scattered debris, plumes of exhaust in the upper atmosphere, and often toxic residues. The space elevator would be gentle on the environment, emitting no pollutants along its journey. The construction and operation would demand vast amounts of energy, but if sourced renewably, especially with the use of solar power, the entire system could be nearly carbon neutral, setting a new standard for green mega-engineering. Yet, the most profound changes wouldn't just be mechanical, economic, or political. They'd be cultural. Spaceflight, once a feat reserved for test pilots and cosmonauts, would become part of our shared human heritage. Children would gaze up not just at a starry sky, but at a glowing thread stretching heavenward. The sight of a constant flow of cargo and people gently ascending, visible even from a distance, would be a continual reminder of humanity's upward trajectory. The elevator would become a symbol, joining great works like the pyramids, the Great Wall, or the Internet as icons of the human will to reach farther and dream bigger. It would challenge the next generations to innovate not just in science and technology, but in the philosophy and ethics of exploring, inhabiting, and stewarding the worlds beyond our own. But the path between dream and reality is full of obstacles. First, the technical ones. Today's carbon nanotubes and graphene fibers can be made just centimeters or meters long, not thousands of kilometers. Factories capable of weaving these materials into such lengths do not yet exist. The technology to maintain, monitor, and repair the cable, to precisely balance forces at cosmic scales, and to keep humans safe during their slow ascent, all await breakthroughs in robotics, materials science, and artificial intelligence. There's also the economic question. Constructing a space elevator will likely be among the most expensive engineering projects ever attempted. Investment would need to be sustained for years, if not decades, and coordinated across nations, industries, and interests. A functioning space elevator would eventually pay for itself by slashing transport costs and opening new economic territories, but reaching that break-even point would require deep trust in technology, patience, and international cooperation. Political hurdles loom as well. Building such a transformative structure can be seen both as an act of peace and a potential spark for conflict. Control over the access point to space, the ultimate high ground, could unbalance today's geopolitical landscape. Only through carefully negotiated, forward-thinking agreements could such a project become a beacon for unity rather than division. Social concerns also demand attention. As with any new frontier, there's a risk that benefits accrue to the already wealthy or powerful, leaving others behind. Thoughtful design of access rights, pricing, participation, and employment opportunities would be needed to ensure the elevator serves all of humanity, not just a select few. Education, outreach, and public engagement would help sustain long-term support and inspire future generations to take part in building upwards. And yet, even with all these challenges, the consequences of success are monumental. A functioning space elevator would kick off what many futurists call the second space age. Daily commutes to orbit, moon-based construction, asteroid mining, and space solar power would shift from possibility to practicality. The resources of the solar system, metals, water, fuel, even living space, would be available to solve problems on Earth, easing pressure on our planet's ecosystems and economies. Imagine a world where electricity flows from orbiting solar farms beamed wirelessly to the ground, where rare Earth metals are mined from asteroids, and where vast rotating habitats provide living space for millions beyond Earth. Imagine natural disasters being predicted with perfect accuracy, thanks to swarms of cheap, replaceable satellites. Imagine a future in which Mars colonies are supplied and Earth is protected from cosmic threats, not because of a lucky technological leap, but because of a deliberate, carefully engineered bridge to the stars. In cultural terms, the elevator might rekindle a new golden age of exploration, a modern echo of Renaissance voyages, but with the whole solar system as the destination. New philosophies, arts, and sciences would emerge, inspired by life at the intersection of sky and vacuum. The psychological horizon of humanity would stretch, and perhaps so would our empathy and sense of participation in a shared destiny. There would be new jobs, new industries, and new problems to solve. Careers in orbital construction, space medicine, zero-gravity agriculture, and planetary science would be as commonplace as those in aviation or information technology today. Schools would prepare students not just for life on Earth, but for a future where humanity is a multi-planetary species. Over the years, the very concept of remote would be transformed. Earth orbit, the Moon, or even Mars would become extensions of our biosphere, their resources and possibilities woven into daily life. Earth's gravity, once an unbreakable anchor, would be rendered optional, a hurdle to be hopped, not a barrier to be feared. And at the heart of it all, silently stretching skyward, would be the elevator, a testament to human persistence, ingenuity, and curiosity. There would be failures, accidents, conflicts, and disappointments along the way. All great endeavors are marked by such trials, but the reward would be a civilization finally able to take a literal step off its home world, forging a path forward not just for its own sake, but for the possibility of life and consciousness to flourish elsewhere in the universe. In the end, the question of what would happen if we built an elevator to space is not just about physics or engineering. It's a meditation on human potential, on whether we choose to reach for impossible heights, to solve impossibly hard problems, and to write ourselves into the story of the cosmos. Before the first climber ever rises above the clouds, before the ribbon shivers with the weight of its burden, before humanity's eyes trace the cable to the stars, there must be the decision to build, to persist, and to dream. In answering the question, what if we built an elevator to space, we confront not just the boundaries of the possible, but the limits of our own imagination, and the extent to which we are willing to shape tomorrow, not as prisoners of circumstance, but as architects of our own destiny. So, as the sun rises for yet another day in the distant future, a gentle, persistent flow of cars glides up a silver thread toward the heavens. Passengers gaze through crystal windows as the earth below recedes and the ink-black, star-flecked sky draws closer. Gravity's hold loosens, and with a sigh, humanity steps lightly out onto the cosmic stage. One humble step at the top of an impossibly tall ladder toward a universe of infinite possibility.